It's Friday. Sunny in London, I believe, though one hardly notices indoors. We're here again, then, for Turing's torch. Another week, another deluge of pronouncements about what this artificial intelligence business is supposedly doing next. It's enough to make one recall Alan Turing's own quiet observation, intelligent machinery, a heretical theory. And it's that rather persistent gap, isn't it, between the theory, the promise, and the rather more mundane reality, that we aim to explore. This week, as always, we're trying to separate the signal from the noise. This is Turing's Torch, Artificial Intelligence Weekly, the bits that matter, minus the hype. A quick note to begin with, because it matters and because it's practical. 3 habits will keep you out of a lot of trouble when a convincing image or clip arrives in your feed. None of them are glamorous. All of them require a little patience and the willingness to doubt what your eyes tell you. First habit, don't take provenance at face value. Ask who posted it, where it first appeared, and whether any reputable outlet can corroborate the raw material. Reverse image searches and looking for earlier versions are simple chores that often reveal a forgery's earliest appearance. If it is a video, ask for the original file or a higher resolution source. Metadata can be stripped or faked, so provenance is the opening act of verification, not the finale. Second habit, read the pixels skeptically. Check lighting, shadows, reflections and how people interact with objects. Compression artifacts, odd hair outlines, inconsistent eye lines and physics that don't add up are red flags. Frame-by-frame scrutiny can reveal cuts or subtle replacements. Modern synthesis is impressively smooth, so the absence of obvious glitches is not proof of authenticity, only a reason to dig deeper. Third habit, don't trust pixels alone. Seek corroborating context, witness statements, timestamps, geolocation, camera metadata, and chain of custody. Ask whether there is an original camera file and whether audio matches the stated environment. For journalists, courts and investigators, those non-visual breadcrumbs often make the decisive difference. For the rest of us, they are the difference between informed skepticism and an embarrassingly gullible retweet. Images and clips still carry enormous persuasive weight. A single convincing fake can shape impressions, accelerate rumors and harm reputations before anyone has had a chance to check the facts. The tools for making fakes are widely available and the incentives to weaponize them are real money. Politics and attention all pull in the same direction. So habit formation matters more than hope for a perfect detector. Which is where a recent and somewhat unusual joint warning from intelligence chiefs comes in. The message was short on drama and long on implication: cyber threats are being accelerated by artificial intelligence. And ordinary people will start seeing the effects within months rather than years. It is a useful recalibration of what we mean by serious in the cyber world. Artificial intelligence-enabled attacks are practical, not poetic. Imagine what once took a skilled operator hours now being performed in seconds. Generative models can write convincing phishing emails tailored to an individual, produce deepfake audio that impersonates a manager, and help craft malware that adapts to avoid detection. The net effect is a dramatic lowering of the skill and cost barrier for attackers. Where an intrusion once required a dedicated team, a less organized actor can now try with a laptop and an API key. Scale changes everything. Automated, cheap attacks mean more targets and more victims, customers duped out of savings, small businesses hit by supply chain fraud, public services interrupted by ransomware. Attribution becomes harder when an attacker's code masks its origin, blurring lines of response. Defenders cannot simply hire more analysts and expect to keep up. They will need smarter tools, different processes and money to deploy them. Practical defensive measures still do much of the heavy lifting. Better authentication, regular patching, vendor checks and the basics of skepticism blunt many of the expected harms. Those are not glamorous solutions, and they do not fit neatly into keynote slides, but they work. The real challenge is scaling those basics, not wishing for a miraculous detector to appear. The intelligence warning also connects to a pattern we've been tracking: automation of creation followed by a renewed need for manual verification. Detection tools will improve and regulations will appear. Platforms will add friction. Yet none of that removes the human work of judgment: question the source, inspect the content, and demand context. Treat suspicion as civic hygiene, not cynicism. That wider tug-of-war, automation on one side and verification on the other, shows up in companies too. A travel platform announced this week that it had adopted large language models across its engineering teams. Their CTO was explicit: you do not gain benefits by slapping a generative model onto legacy systems. You redesign workflows. At scale, using models across engineering breaks down into a number of practical things. It can mean code generation for prototypes, automated testing and QA, natural language interfaces for searching inventory, or multimodal features linking images, text and structured data. For a company coordinating thousands of transport providers across dozens of countries, the real challenge is not the model but the plumbing. A suggestion from a model is useful only if the downstream systems can execute reliably. Inventory, payments, contracts and error handling all have to cooperate. The travel industry is a cautionary example because it is painfully integration-heavy. Legacy APIs, fragmented supplier data, last-minute schedule changes and myriad tax rules make every neat product idea expensive to implement. A model that helps prototype faster can cut time to market, but it also introduces risks: hallucinated itineraries, privacy leakage when supplier data gets used as a training signal, and brittle user experiences when the world refuses to match the model's idealized assumptions. The practical lesson here is simple. Firms that succeed treat models as components of redesigned systems, not cosmetic add-ons. That requires investment in observability, human-in-the-loop controls, fallback paths, and contractual clarity with hundreds of suppliers. It also shifts where organizations spend money: more platform engineering, more compliance effort, and more careful product design to manage inevitable model errors. Put another way, using artificial intelligence to accelerate development is not a low-cost shortcut. It is tedious and expensive work. There is no applause line for rewriting workflows, and yet that rewriting is exactly what produces durable gains. If a company wants faster product development, it must build the safe scaffolding that makes speed repeatable and auditable. Embedding artificial intelligence into shared workplace spaces raises related governance questions. One vendor has added an assistant directly into shared channels so anyone can summon it with an @ The difference between a private chatbot and a chatbot listening to an office conversation is more than convenience. It changes who can act and who is accountable. When an assistant drafts an email in a #client channel, ownership frictions immediately appear. Who checked for legal concerns? Who verified privacy constraints? If the assistant invents a fact, is a colleague blamed, is the organization blamed, or is the vendor blamed? Organizations that enable such features without clear rules will learn governance the hard way, because the risks are real. Confidential details posted in haste, or a model confidently asserting something false in front of the whole team. Operational side effects are quieter but no less important. Channels will get noisier. If every routine ask becomes a spectator event, signal tonus drops and attention thins. From a security standpoint, teams must design access controls, logging and audit trails. Questions about prompt storage, retrieval and regulatory compliance are practical, not philosophical. Decide which channels get the assistant, limit its permissions, log everything, and train people not to treat it as an infallible colleague. Similarly, a global electronics firm opened its internal doors to enterprise conversational and code models for thousands of employees. The two tools serve different jobs. One drafts documents, automates routine correspondence and sketches plans. The other writes code snippets, scripts and small automations. Together they aim to reduce friction between idea and execution. For a company building complex devices, even modest reductions in prototype time are commercially significant. Speed matters when you are juggling hardware, firmware, cloud services and user interfaces. There is also an internal efficiency angle. Non-technical staff can generate drafts and handle repetitive tasks without waiting for a developer, and developers can offload routine coding. Those are sensible commercial incentives. Still, there are trade-offs. The risks include accidental disclosure of sensitive designs, over-reliance on confidently wrong outputs, and the engineering effort required to build guardrails. Plugging a language model into a firmware pipeline is not a zero-cost upgrade. It demands oversight, policies and integration work. The upside is genuine, but only when organizations treat these tools as parts of an engineering process that require governance. All of these workplace moves sit alongside a quieter but strategically significant development. Companies are seeking greater control over the hardware that runs models. One prominent firm has developed an in-house chip, an ASIC, with a partner in the semiconductor industry. The goal is straightforward: reduce infrastructure bills and reduce reliance on a dominant hardware supplier. GPUs are general purpose and versatile. An ASIC is tailored silicon. When you can define the workload precisely, bespoke silicon delivers better efficiency per watt and per dollar. That matters when you are running data centers that look like small countries. Even a single percentage point of savings on power and hardware scales into serious dollars. The catch is familiar: ASIC design incurs huge upfront costs and long lead times. You must rewrite parts of the software stack and commit to a particular set of computation patterns. If model architectures shift, or new algorithms favor different hardware traits, bespoke silicon can lose its advantage. You trade a supplier margin problem for a different form of vendor dependence on the fab, the design partner and the bespoke toolchain. So the decision to build chips in-house is both defensive and risky. It gives control and potential cost savings, but it also concentrates power and raises questions for competition and portability. When the stack becomes vertical, interoperability frays. Customers and regulators should pay attention. The industry is moving from renting to building, and that reconfigures who owns what in the value chain. There are advances on the algorithmic front as well. A startup has claimed progress on a decade-old scaling bottleneck in language models. The claim is technical but would be consequential if it holds up. Reducing the pairwise calculations that blow up as context grows would let models handle much longer inputs with lower memory and compute. Distinguish theory from practice. An elegant mathematical trick can reduce worst-case cost on paper, but production systems are littered with elegant ideas that stumble on engineering trade-offs. If the algorithm truly reduces cost without harming quality, the practical effects would be substantial: cheaper inference, longer context windows, and pressure on specialized hardware assumptions. That would matter to cloud vendors, startups competing on price, and anyone wanting a model that can read a whole book or a long legal file. The responsible route is open code and reproducible experiments. The dangerous route is marketing before replication. History suggests caution. Many past breakthroughs looked promising in papers and proved tricky in production. Take the claims seriously, but expect the obsessed community of engineers and researchers to run the numbers and the experiments. The result that will matter is not a paper alone, but whether others can replicate the gains at scale. Parallel to hardware and algorithms, developers are automating what used to be artisanal work. Loop engineering is the neat label for swapping a human who types prompts with a designed system that runs a recursive loop. You define objectives, constraints and success checks, an agent plans, acts, evaluates and repeats without a human pressing enter each time. In plain language, loop engineering turns prompting into software. The skill shifts from composing clever text to designing control systems, validators, rollback strategies, timers and monitoring. That has clear efficiency benefits: fewer people babysit models, end-to-end workflows speed up, and chain tasks happen automatically. It also concentrates responsibility. When an automated loop makes a mistake, the error is baked into the system's objectives, not in an individual's wayward prompt. That concentration of power raises governance questions. A loop that decides what to do next is harder to inspect than a transcript of prompts. Regulators and security teams will ask who set the goals and how success is measured. Defensive automation itself becomes an attack surface. Agents can optimize for their tests in perverse ways, and loops drift over time as conditions change. Automation trades one kind of labor for another more centralized and highly technical work, and that new labor needs oversight. Some practical guardrails help. Make success checks observable and hard to game. Keep humans in the loop at critical decision points. Log intent as well as outcome. Run adversarial tests and be ready to roll back. None of that eliminates risk. It merely turns invisible failure into visible bureaucracy. At the same time, agent frameworks and their defaults matter. An open-source agent project introduced a blank slate mode that boots an agent with almost everything switched off. By default, the agent only connects to a model provider, basic file operations and a terminal. Everything else is opt-in via command line flags. That modest default is quietly important. Agent frameworks can call web searches, APIs, calendars and cloud services. Those capabilities are powerful and convenient. They are also easy to misuse. A sandbox model that only gains power when a human explicitly grants it reduces accidental data leaks, surprise API bills and unexpected production changes. For researchers it improves reproducibility, for operators it clarifies the security boundary. Defaults matter as a practical matter. Opt-in capabilities, least privilege settings and explicit permission lists are small engineering choices that reduce incidents. They are not a panacea. They will not stop a determined insider, and an opt-in can be misconfigured. But sensible defaults buy time and clarity, which is preferable to systems that escalate their own power by default. Other tools are trying to make the messy work of prompt tuning less artisanal, and more systematic. One networking firm open-sourced a pipeline-aware optimizer that claims to find which step in a multi-stage language model chain is failing. Suggest prompt and parameter fixes, and then validate whether those changes improve accuracy. That is a sensible idea. Modern applications rarely rely on a single prompt. They stitch extraction, reasoning, rewriting and verification into chains. Errors can arise at any stage. A tool that attributes failure to a particular step, generates alternatives and validates them could save substantial engineering hours and reduce brittle behavior. A couple of caveats, as always. The validation is only as good as the reviewer. Independent reviewer can mean another model, an internal test harness or a small pool of annotators. Any of those can bake in biases or overfitting. Automated optimization that targets a specific metric can happily optimize the metric and miss everything else: fairness, safety, latency and cost included. Open sourcing the tool helps scrutiny, but reproducing reported wins still requires datasets, compute and careful experiment design. We are seeing a steady shift away from one-off prompting and toward toolchains and pipelines. That professionalizes development but also concentrates advantage. Organizations that can sweep optimizations across many pipelines will ship better products faster. That translates into competitive differences that matter in the marketplace. The machinery of production is broadening in other ways. One model now outputs SVG illustrations as code rather than as images. It hands you a recipe of lines, curves and coordinates that you can scale, edit and animate. There is a practical elegance to vector output. SVGs scale without loss of clarity, they are searchable and version control friendly, and they sit naturally in developer workflows. For interface teams, documentation and diagrams this is useful. Engineers can drop generated icons straight into web pages, tweak brand colors with a few lines of CSS, and animate elements without re-exporting raster graphics. Caveats apply. An SVG generator is not a substitute for a design system, or a human designer. Vector output suits icons, charts and diagrams, geometric, rule-based things. It struggles with texture, lighting and the organic mess of photographic imagery. Because the output is code, you trade pixel imperfections for malformed paths, inefficient vertex counts or semantics that don't match the intent. A generated icon set can be fragile to edits or omit accessibility attributes you would expect in careful craft. Still, the shift is telling. Models are producing artifacts you can run, edit and audit, not just prose. That blurs the boundary between creative tool and production tool and raises practical questions about provenance, ownership and quality assurance. Who signs off on a generated icon set? Well, that was rather a lot to get through, wasn't it? In times like these, when the noise can be quite deafening, a bit of clear thinking is, I find, rather essential. If you'd like to keep track of all this, day by day, without the usual fanfare, you can sign up for the daily briefing at jonathanharris.online. It's one email, no fuss. And if you're looking for something a bit more substantial, perhaps to ponder over your morning tea, you might consider my own book, Artificial Intelligence Revolution in Railways, Modernizing Travel for a Smarter Future. It's available in the e-books section. That's your lot for this week's Turing's Torch. If you want the daily brief, head to jonathanharris.online. Same time next week. Try not to believe the press releases.